basically wherever, jets in GRBs, jets in, and now jets in common envelopes. Okay, and so apart from Fabio and Enrique, we joined forces with Sagib, that's in LSU, and Roberto Iaconi, that he's out of academia now. Right, so Enrique already showed this plot on the left, and basically what it's saying is the fraction of stars that are in either isolated, here this red line, or that are in binary systems, which is the green line, in triple systems, which is the blue, and in quadruple systems as a function of the most massive star in that system. And so if you see, the more massive a star is born, the more it will be, the less it will be in single, isolated, and the more it will be in binary, triple, and quadruple systems. So basically, many, if not most, of the stars are born in binary systems or more, and especially massive stars, those above 5 solar masses. We think that more than 70% of the massive stars are born in binary, triple, or quadruple systems. So binary evolution is really, really important. Not only that, but also here, now I'm showing the fraction of these stars that will interact. And also, as you see, around, I don't know, more than 5 solar masses, basically 50% of those massive stars will interact. And when I say interact, what we're meaning is they can either, and here this is a nice plot that Fabian Schneider did that. So they will either, there will either be mass transfer from the most massive to the other member of the binary system. They can merge if they're born really, if they are very, very close. But also there can be this phase that's called common envelope, which is really easy. There's the most massive star has a really big envelope, and this envelope will be common to both stars. Let me just explain a bit more. So common envelope is this phase I'm showing in the video. What is it? It's like a 7 solar mass star here, and there's in this case, there's a compact object. It's a neutron star. And so I'm going to be showing how this, sorry, let me take the music off, how this is evolving. And so common envelope is a very interesting phase that comes in, that may be present in the evolution of a binary system, especially when one of these stars is very massive. The bad news is that it is really short. So the constraints that analytical constraints are of the order of 1,000 years, but numerically we've seen even lower values that they last hundreds of years. So that's why they're so difficult to obtain, to observe. We haven't really observed one system which is in the common envelope. We've seen post-common envelope objects, but not in the common envelope. Okay, and so also a very interesting thing of common envelope is the evolution that they have. So here I'm presenting 3 pathways, evolutions. Don't worry. I'm gonna just talk of how they begin and how they end, these 3 evolutionary paths. In one, it's like a 8 solar 0H main sequence object and like a 15-ish. And in the end, this one ends up producing a short gamma ray burst. This one, by the way, is done by William and Enrico. In the other, it's a super giant and a main sequence. And in the end, it has many pathways and it produces supernova type 1A. And the other last one is Nobel Prize it's two very massive main sequence, and in the end, they end producing the 36 and like 29 binary black hole merger that produced the first gravitational wave that we detected. And in all of these phases, which, by the way, these can be observed, or there can be the optical counterpart that Colibri may observe. In all of these phases, there is the common envelope present. And so the truth is, we know very little of common envelopes, but they are very important. It is very important. Also, sorry, this one I'll skip. There's another evolutionary path also in which there's low mass X-ray binaries, high mass X-ray binaries, and there's always common envelopes present. So it's really important to produce high energy astrophysical phenomena. And when I said that we don't really know perfectly this, there's many models in order to explain which is like the main driving mechanism present in the common envelope. And this is the most discussed and very well, yeah, it's like a fraction of the orbital energy converts and is what liberates energy and destroys and stops the common envelope. But apart from this fraction of the orbital energy, there's ionization, there's the so-called gamma prescription, there's nuclear energy, dust, accretion, magnetic fields. And in all of these, there's difficulties in order to terminate the common envelope. And so this is when Fabio, Enrique, and myself came into here. And since we love jets, there's room for jets in the common envelope evolution. And so this is not our first idea. There's many, Chevalier, Noam Socker and his group. So jets inside the envelope, the common envelope of a red giant or a super red giant. And so here, specifically what we studied is jets launched from a main sequence star, and all of that inside of a red giant. So I'm not going to get very technical. There's two groups of the numerical people that they either do very large scale studies in which you see the whole evolution, but the resolution is not that good. And then there's those of us that do small scale evolutions, and we have really nice resolutions, but we don't see the whole picture. And so in this study, what we did is we merged forces. And so we took the simulations from Sagiv and Roberto, which is these large scale, and we focused on some cases of this large scale. So we're doing jets from a main sequence star, all of that in a red giant, based, well, and small scale, but based on the large scale simulations of Sagiv and Roberto. So we're trying to, to like understand the whole topic. And so the numerical setup, I'm gonna go sort of fast. If you want, I can focus more later on this. So we have the red giant. It's like a 1 solar mass, and it has like 100 solar radii. And in this, we put a main sequence star, which is launching the jet. The main sequence is like a low mass main sequence, 1/3 of a solar mass. And we analyze this in 3 specific moments. Either when it's in the border of the red giant, which is called grazing. And so this is the grazing envelope phase. And also when the main sequence star, which is launching the jet, is inside of the red giant. And so it's either, we call it when it's already plunged in, and in 2 phases, moments when it's 3/4 of the radius and when it's like halfway of the radius of the red giant. Okay, and we launch the jet in 2 forms. One is the jet can either be constantly powered, and in another it's self-regulated. But we found that there's really no big difference. So don't focus on this. But for the referee, this was a big issue. And of course, we're doing small scale. And so we're focusing on what's happening very close to the main sequence star. Right. And technical stuff also, we used Fabio's mezcal code. So for those of you who don't know, mezcal is like the fancy, trendy tequila that we drink now in Mexico. And so it's a nice name. And also another important thing is we're not looking at the big picture where our reference system is in the main sequence star. So our reference system is locked. And so we see like a wind, which is incoming because the main sequence star is moving around the core of the red giant. We simulate like 11 days, and the jet is powered with different efficiencies. And all in all, we do 30 models. Okay, and so I'm showing like the basics of these models. This is like when we're grazing, this is the meridional view, this is the equatorial view, and we see that in this case, the jet is very efficient, and in there we will see it, and it's like pushing, blowing material from the border of the envelope. And what else have we done? And here, where it's plunging in, then, and also as you see that our main sequence star is actually moving inside of the red giant. And so the basics is when we're in the border, the jet is very easily launched, and it takes material from the border of the red giant. And here, so it only needs 10 to the 30, it only needs 10 to the 37 ergs per second to be successful, but we don't see a clear disk forming around the main sequence star. On the other hand, when it's already plunged in, the further in it goes, the more difficult it is for the jet to be successful, because there's very dense material the further in you go. And so the jet is actually not able to beat the ramp pressure of the material which is there. And actually the material, because it's actually, there's a fraction of this material that's been accreted by the main sequence. And so the jet is not able to beat that ramp pressure. And so the further in you go, here you see there's no jet. And in the middle part, in this middle plane, we can have successful jets, but only if they are very efficiently powered, if they have like 10 to the 39 ergs per second. And once more, in none of these cases, we see clear disks. And so I mean, you may be thinking, what the hell does it have with Colibri? Yeah. And so the point is, the material that is ejected in this part, this is not the best part of the paper. We did like a, how do you call it, a napkin calculus to see the temperature and like in what energetic band this would be visible, and we saw that it would be either in infrared and maybe in optical. But take this with pins. We have to do still further studies to put observational constraints in this. And also another thing that is very important is we really don't know what happens near the accreting object. And so Enrique a while ago was mentioning Eddington, or was mentioning Bondi accretion rates. And so what we saw and what we can really say is that the accretion rate that is being accreted by the main sequence star is like 1.1% to 5% of the Bondi-Hoyle accretion rate, which is very important for those of us who are interested in the jet that is being powered. And then also we saw that it's really difficult to form an accretion disk. And so here comes the problematic of, if there's no accretion disk, then the jet is difficult to be powered. Or it's not going to be powered by Blanford. I always get it wrong. Blanford, Snayek, or Blanford Payne. There has to be some other launching mechanism, magnetic fields, or there's other stuff like Noam Soker mentioned, like accretion belt, that we do see something like that. It's more like a belt, not a disk. So it has to be some other exotic way, not exotic, some other way instead of an accretion disk which launches a jet. And so, since I have very little time, I put my conclusions. And so we studied a jet from a main sequence star in a red giant with joining forces with large and small numerical domains. And we saw that if you're in the grazing part, it's really easy to launch a jet or for the jet to be successful. The further in you go, the more difficult for the jet to be successful. And of course, further studies are required to match all this stuff with telescopes like Colibri. And with that, no, wait. And so thank you very much. And I hope we meet next time in person. And for those of you who are in the US, happy Thanksgiving. Thank you.
Okay, so anyone have questions? So Stefan, please.
Yes, a small question, a very technical question. As a previous slide, Diego, just to no, the conclusion. The last sentence is the most important for me because it's a very nice object, a very nice analysis. But when do you plan to give some observational constraints to us? Because I suspect that you have so many degrees of freedom in your simulation that how can we distinguish? How can we extract the parameters of these systems?
Yeah. So honestly, that more of a question for me. That's a question for Fabio because it's also we need sort of better radiation transport. Here, the only thing we could sort of calculate is the optical depth, and we calculated for the material when it's tau equal to 1, what temperature there would be there. So we saw that it would be like a black body in infrared or optical, but we do need more of that. So I'll pass this question to Fabio so that we improve this analysis, Stefan, and so we can have a more.
It would be interesting to have them because it can have consequences in terms of time sampling and so.
Yeah. And of course, this with Rubin, with Vera C. Rubin Observatory, we're going to observe tons of, well, hopefully, tons of common envelope, also transitories.
But it's a funny object.
Yeah, my point is, so we should keep in track not only the optical counterpart of neutron star collisions or supernovae or stuff like that, but also common envelopes. Let's put that in our mind.
Yeah, I will. No, it's very nice.
Okay, I think that nobody else have questions. But before we continue, I have one. So, what is the range of masses for the stars in which your results have validity?
So for the common envelope, you mean? Sorry.
So
can you hear me? Or did I mute myself? Okay, no, good. So
0.88 solar masses for the primary and 0.3 for the secondary, but the results have the same validity for a star with 10 solar masses for the primary, or? So
here we're analyzing the red giant. There's other groups that analyze if it's not a red giant or a red supergiant, and it actually seems that it's easier for the jets to be important in that phase. But then also, as Enrique said, binary evolution is a zoo, and so what we're seeing is if the central star, which is accreting, is a main sequence star, for the jets to be important, it seems very difficult because there's no accretion disk. But we've also done the case in which the accreting object is not a main sequence star, but instead a neutron star or a black hole. And what we see is in those cases, when the accreting object is a 1.4 neutron star or a 5 solar black hole, oh boy, you do form an accretion disk, and there the jets are more important. And so my answer is it depends. So what we're seeing is for main sequence stars, it seems it's difficult for the jets to be important. But if you have a compact object, then it seems that jets are really, or may have a really important impact. And then also, it seems that the bigger your star, the easier also for the jet to be important. And so we need tons of simulations or evolution simulations with MESA or something like that.
Okay, so thanks Diego again. And with this talk, we end the other transients part. So let's start with the GRP part. The next is Nisim Fraija. I don't know if Nisim is